So next up, we have Professor Bingqing Cheng, who's an assistant professor at UC Berkeley, working in the area of computational chemistry. So over to you, Bingqing.
So thanks everybody, and for me it's my great pleasure to kind of say hi to the UK community. I was a postdoc fellow in UK, so this really brings back the fun memories, and it's also great to see the many familiar names from the talk of Yuxing. So Yuxing's talk really set a very nice stage for this one, because he already mentioned the powerful paradigm change brought by the machine learning interatomic potential, and that unlocked many applications. So in my group, we did things, for example, like phase diagrams, mixtures, interfaces, and transport properties, and so on. And I just want to spend a couple minutes talking about the underlying architecture of a state-of-the-art machine learning potential. So whether it's ACE or MACE or GAP, it can be understood from a graph representation. So the atoms are nodes, and if the two atoms are within a certain cutoff radius, they are considered to be connected by edges. And then one just have to featureize these edges, right? So it depends on the element type of the two atoms it connects. It depends on the distance, radial distance. Usually one use a radial basis. And then it's the orientation information. So in GAP and in ACE, people typically use spherical harmonics, and spherical harmonics is also what's underlying in E3 and N and so on. But this is actually not the only way. So in the Cartesian atomic cluster expansion, so what we did is that we essentially reformulate atomic cluster expansion, but completely in the Cartesian coordinates. Now, if you're familiar with like atomic cluster expansion or the E3NN framework, you know that they use spherical harmonics, and then they also use Cage-Gordon tensor contraction to do the symmetry operations. So in Cartesian coordinates, there is really a correspondence, very clear correspondence between the Cartesian, the Cartesian angular momentum and the spherical harmonics. For spherical harmonics, we need the Cage-Gordon tensor contraction, but you can do everything in the same way in the Cartesian coordinates, and all you need to know is the multinomial theorem. So here I just found actually on Reddit, there's a graphical representation of the multinomial theorem. This really underlines all tensor operation. So for example, you can do a like vector dot product, again, proof using the multinomial theorem. You can do a vector addition this way, again, like from the algebraic manipulation from the multinomial theorem. Okay, so after that, we can optionally do some message passing. We can then symmetrize our orientation dependent representation to make an invariant form. And then these invariant features for each atom, for atom I, is then read out through a multilayer perceptron to give us the local energy. And then we can just sum over all local energy to get the global energy. And the forces are just the derivative of energy with respect to position. So this is really the underlying construction for most of the machine learning potential we are using today. Now, the issue with that is that all these potentials are more or less short-ranged. And then let me give you an example. So let's say if we have a system like that, right? So we have two molecules, and one is positively charged and one is negatively charged. Of course, we know that there will be very strong Coulomb interaction between them. They almost behave like two naked charges. However, We also know that if the two molecules, their distance is beyond a certain cutoff, they will not interacting. And even if you use many message passing layers, if the separation is big enough such that the two molecules live on separate molecular graphs, message passing not gonna save you. So just as an example, so this is machine learning potential with message passing. You see that after some separation, after some distance, the energy becomes flat, which is of course very unphysical. And our long-range machine learning potential can solve this. So let me just unpack what we did. It's actually exceedingly simple. So remember that we have these invariant features in our short-range machine learning potential, which we use to read out a local energy, EI. So here, we just reuse the exact same features, and then we read out a latent charge. Now, for finite systems, we can just use these latent charges to compute the electrostatics using the pairwise summation. And then for finite systems, we can then use Ewald summation to get the long-range energy. Then we just add this long-range energy to the short-range total energy that the machine learning potential is by itself can predict. And then that's our total energy. Now, when we are training the network, the loss is exactly the same as the short-range only machine learning potential. So we just train on the total energy. We train on the forces and sometimes stress as well. We do not train on charges. Charges are learned indirectly. Okay, so this solves the dimer binding problem. And then, so this dimer binding problem is a very obvious kind of a case that short-range potential would fail, but there are other more subtle cases. Now, for bulk water, which we have historically also modeled use a short-range potential, and people also think for water, the long-range interaction shouldn't matter because of screening. However, if you want to compute, for example, the dielectric constant of water, right? So you do the dipole-dipole correlation function, a different wave vector, and then this guy extrapolate to the k equal to 0 limit, essentially gives you the dielectric constant. Now, if you use a short-range machine learning potential, like one ACE layer, you get you will have actually a divergence at k equal to 0 limit, which I call the dielectric constant catastrophe. If you now use message passing, the phenomenon persists. It kind of delays the onset of the divergence, but does not really solve the problem. Only the long-range potential gives you the correct asymptotic behavior. Okay, so here's another example about interfaces. So we have here we have a titanium dioxide slab, and then in the water sandwiched in between, we have a electrolyte. So this is a sodium chloride in water. Now, if you use a standard short-range potential, it predicts something that is highly unphysical. So here we are plotting out the ion density along like this, like perpendicular to the interface. And you see in the bulk region, in the center of the slab, you have an axis of chloride ions compared with sodium ions. This, of course, would have introduced a huge electric field, and it's highly unphysical. But the short-range machine learning potential doesn't know that. And after using less as the add-on, you see that we are recovering the correct behavior with the ion density balance. Okay. Historically, there has also been other schemes do long-range interactions. So, for example, load is one of them, and that's and also there's a long-range density descriptor. So these are essentially based on projecting atomic density descriptors in the reciprocal space. Now, however, like less, which is very much simpler, actually perform better in terms of accuracy. There has been also a different school of thought, and that originated from the pioneering work of the fourth generation of the Baylor polyneural neural network. So the idea there is that you can explicitly train on DFT charges followed by a charge equilibration scheme. However, like we tested the data set they used, we realized that if we just train on energy and forces and not train on charges, we actually get a accuracy that is actually in most cases much better. In this particular case, it's like 1 order of magnitude more accurate compared with the schemes that explicitly train on DFT charges. And this was also the moment that got us thinking, because okay, so we are not training on DFT charges, but at the same time, we do have this notion of latent charge in our method. So what does our latent charge mean? Does it have any physical meaning, right? So to test on that, we just look at a toy system. So this system is an electrolyte, so it has bulk electrolyte and also electrolyte air interface. So we just compute the energy and the forces from a classic empirical force field with fixed charges. So this is XPC water and fixed charge ions. And then we just train on energy and forces. And we realize, okay, just use tens of examples, we can recover the true charge. Now, in this case, you might be wondering, okay, but in this case, because you are having a classical fixed charge model, these charges are, you know these charges, these are the ground truth. But for a generic case, for if you have DFT, and then actually the DFT charges are not physical quantities, right? So different definition of DFT partial charges actually gives you different values. Now, when we compare our less charges to some definition of DFT charges, we see that they are correlated, but they are by no means the same. And in fact, if you compare between different definitions of DFT charges, they are also like correlated, but by no means the same. So for example, if we compare MBIS charges and Mulliken charges, Hirschfeld charges, you see they're all correlated, but they're not the same. However, what's interesting is that all these charges, including the less charges, predict the correct dipoles and multiples of this gas phase molecule. Now, like in contrast with partial charges on an atom, like the dipoles and multiples are actually physical quantities, right? And then this is also, so this is for gas phase molecule. Now, what about bulk systems? So for bulk systems, what the charges we are learning is actually the scale charges, because we can think of atoms have free charges, and then the interaction between these free charges are screened by the static dielectric constant, often also called electronic dielectric constant or high frequency permissivity. So these are screened by the background of like the free electron. So our learned charges are these scale charges. Now, if we are in vacuum, then this is just a constant of 1. Now, if it's kind of a bulk system, right? So we need this constant number. This is just a one constant number for one system. And the square root of static dielectric constant is actually just the optical refractivity. So one can obtain this either experimentally. So for water, it's 1.33, if I remember correctly. And if it's not known, you can also just perform a single point of density functional perturbation theory to get this epsilon infinity. Okay, now for the polarization for a system without periodic boundary condition, the finite system is just the R dot Q, and then we can also obtain the so-called Born effective charges. So the Born effective charges can be written down in two ways. One is the derivative of polarization with respect to atomic position. It's a tensor. It's a 3x3 tensor. It is also related to the response of the system to external electric field. So let's say if I add an external electric field to the system, right? So I have atom, I add external electric field. So there will be a response force on each atom. So the Born effective charge is also related to the response force in response to the external electric field with respect to the electric field. So this is a physical quantity that can be computed and can be measured experimentally. Okay, so this is for system without periodic boundary condition, but what about with? We know that for a periodic system, the polarization is actually not well defined because there's the multi-valued problem as also explored in the modern theory of polarization. Now, in this particular case, for periodic system, we use an extended definition of polarization and use this form to obtain the Born effective charge. So the derivation here is very analogous to the Barry phase in quantum mechanics. So okay, so let's put this theory to test. Now, for this system, what we did is that we have a very small data set of bulk water. This is just 100 snapshot of water molecules. We see that we plot out our predicted less Born effective charge and compare to the DFT ground truth. Now here we need to pay attention, right? We really need to use the PBC corrected form. If we ignore the periodic boundary condition because of this multi-value problem of polarization, you have some predictions, especially for atoms next to the edge of the box, it will be off. But if you use our Barry phase corrected expression, you see your Born effective charge will be spot on. Now, the Born effective charge is related to a number of physical observables because it's essentially the electric response property. And one of the things one can compute very easily is the infrared spectrum, because that's essentially the autocorrelation function of polarization. Now, here, again, using the same network, we are able to predict the water IR. And more than that, we can also compute the what are on the electric field because the Born effective charge also allows us to add to exert to impose external electric field to the system. So here's another example. So many years ago, I computed this phase diagram of superionic water. So for doing that, there was a very diverse training set, and then the reason for that is that you see this phase diagram spans a very wide range of temperature and pressure conditions, so up to hundreds of gigapascal, and also the temperature ranges like from 0 to 5,000 Kelvin. So very diverse configurations. It also contains many ice phases. So we have the familiar ice 10, where you see that the oxygen atoms form a BCC lattice and hydrogen are shared in between. And then we have superionic BCC, superionic FCC, superionic HCB, and we have ionic liquid. Now, we just take a subset out of this original data set, and then we train our long-range machine learning potential. And in this case, we can recover the correct Born effective charge for all phases, for all explored phases. Like in a very wide range of density, pressure, and temperature. So the Ball-infected charge, another use of it is that it allows us to compute the electrical conductivity, because you can either do it using the Green-Kubo relationship from the autocorrelation function of the electric current, or you can again do in molecular dynamics under external electric field. So you put your box under periodic box under electric field and monitor how fast the ions move. So another application, so this is a very tough system to work with. So this is a ferroelectric material. Now, it has in a condensed matter community, it always has been a little bit of mystery why the ferroelectric material have like anonymously large Ball-infected charge. You see that, for example, if you look at the Ball-infected charge of oxygen. So the oxidation number of oxygen is like -2. But you see the diagonal value of the Ball-infected charge actually massively exceed that. So it has always been a little bit of mystery in DFT why this is the case. But just by learning from energy and forces, we can recover this trend and have a semi-quantitative prediction for the Ball-infected charge. And then with this, we can also do some simulations. So first of all, like if we do not, when we simulate a system like this, if we do not add any electric field, we can recover the correct spontaneous polarization of the ferroelectric material. So that's this one here. And then we can do something fun, right? So here we have already the polarization. We can now add external electric field to see how the external electric field affects the polarization of my material. And from this, we can simulate the hysteresis loop. So let's say if originally I have like spin up, I can put the opposing electric field to make it spin down and look at the hysteresis. And we can also look at the mechanism for this polarization switch. So here, originally we have spin up. Now we add external field to make it spin down. And you can see that the mechanism is via the nucleation of small domains of the opposite spin. And then these domains would grow and coalesce, and finally the spin of the whole system flipped. Now, historically, we have implemented less into our short-range machine learning potential case. Now we have also implemented as a plugin that is compatible to any short-range machine learning potential. So we have actually already done the implementation of that for Maze, Niquib, Allegro, UMA, and ChargeNet. So for Maze, it's already incorporated in the main branch of Maze. So if you're already using Maze, you just need to use the latest version from their main branch of their Maze repo. And the Maze less model should work out of the box. And for Niquib and Allegro, it's implemented as an extension pack. You can use it in the same way as if you're using Allegro. Okay, and with the plugin, so with this plugin, it's very lightweight. It also only adds a tiny, like a tiny computational overhead. So here's a comparison. So again, coming back to this system of order, we just tested many short-range machine learning potential, including Maze, Niquib, ChargeNet in case. You see that adding the long-range correction uniformly improve the performance of the model, and most importantly, in all of these cases, we can recover the Ball-infected charge. So it's just another example and the same trend. So we always it always help with the accuracy, and we can always get the accurate prediction of the Ball-infected charge. So here's a very recent trend actually not that recent, started like maybe a year and a half ago, is to like before the tendency is like if I'm interested in a system, I make a bespoke machine learning interatomic potential for that system. Now, right now the trend is to make a so-called foundation model. The foundation model here means that it's a general, or sometimes it's called universal machine learning potential that works across the periodic table, can be used for a variety of applications. So the most well-known ones are probably Mace MP0. So that's the earliest one. That's one of the earlier ones. And the latest one being like very popular being UMA. So this also this one that is called Maze Off. So that is fitted it is fitted to the SPICE dataset. So that's a dataset of small gas phase molecules and also some water clusters and other clusters. And then it's being used for a variety of applications, including molecular crystals and proteins and so on. So just to test what does less do at scale. So we also fitted maze, what we call the maze less off. So exact same training set, and then we use the same maze backbone. And you can see that, so here we are, so the maze off has different settings like small, medium, and large. So when you, they differ by cutoff and also the complexity of the representation. So the small is very fast, and then medium and large becomes more expensive, way more expensive, and also more accurate. Now, here we are using a setting that is quite similar to the small model. We use the same 4.5 angstrom cutoff, but you can see that we are hitting an accuracy that is very similar to the Maze large model. And compared to the Maze, we also have a speed that is very similar to the Maze Maze of 23 small. More importantly, in all cases, we can accurately predict like molecular dipoles as well as BECs. So we can also predict the BECs for bulk systems, and that again allows us to make predictions such as water IR. Now, Maze of 23 is really a very impressive model. But one thing that was that they didn't do particularly well is the prediction of for the density and vaporization enthalpy of bulk organic liquids. And this is also quite understandable because this is actually a huge extrapolation task. Because the SPICE training set is completely on gas phase molecules and clusters. So extrapolating to the bulk is already by itself an impressive extrapolation task. Now, Maze-Off has a little bit of a systematic offset in the prediction of the liquid density and vaporization enthalpy, and somehow adding less correct these. And another thing is that the long-range electrostatics would affect things such as protein folding. So we are folding like this protein. You can see that Maze less off and Maze off actually folds this protein at two different states. So indeed, so the Maze less off, the final state is more similar to what Amber would predict. Okay, so in the last 5 or so minutes, I'm going to go through another example. Is like the latest application. So this is about the electric double layer. So this is about electrified electrolyte interface. So our system looks like this. So we have two metal electrode and then which sandwich some electrolyte solution. Now, LESS by itself cannot model the long-range charge transfer on metal surface because that's in principle infinitely ranged. But one can couple LESS to like charge equilibrated, essentially the Siemens-Brick metal model. So the charges on metal are determined by the classic metal model that assumes that the metal is a perfect conductor, which is not a bad assumption for platinum that we do here. And then the electrolyte, the charges are described by less. So with that, we can also perform constant potential or constant electric field simulations. So essentially, for imagine if you have a capacitor, right? So you would have different electric potential on the left and on the right electrode. You can also opposing the same thing by adding a constant field to your simulation. So by doing that, we are able to simulate the structure of the electric double layer. So for the simplest case, so this is water and the platinum under no external electric field. So on the surface, you basically see two layers. One is the so-called chemi-soft layer. So the water, water is essentially bonded to the platinum, and then the second layer is usually called a physio-soft layer. So that's a very high density, and then the density of water decay to like around 1 gram per cc. So so we can also plot out we can also investigate the dipole distribution in different layers. So in the bulk, it essentially forms a random distribution, but on the surface, the water is kind of highly orientationally anisotropic. And we can also investigate the water density distribution on the surface. Here is just like a density map. So in the chemically absorbed layer, the oxygen, the red here, is essentially directly sitting on top of platinum. It's bonded to the platinum, and then we have like hydrogen atoms. The chem absorbed water is essentially kind of lying flat on the surface, so therefore the hydrogen kind of form a ring-like structure around the oxygen. So such density ordering is almost disappear in the physically absorbed layer. So we can do this, first of all, at different external potential. So here, let's just look at water. So what this plot showing here, the phi of V, the phi as in the unit of volt, is like the 1D electric potential across the interface. So we have the two electrodes, how they're different electric potential, and then we are looking at the potential change across the interface. So most of the change are happening at the electric double layer region, consistent with the classical picture. Now for water, because it's dielectric, in the center you have a small slope of potential drop, indicating a finite electric field in the system. The external potential would also alter the distribution of chemi-absorbed layer and physically absorbed layer. Now we also add a little bit of salt in water to make it an electrolyte. Now, the biggest difference here is that you see in the bulk region, the potential surface is completely flat. This is because, and indicating there's no electric field in the bulk region. So this is because the ions would redistribute and screen all of the electric field in the middle. So from the charge accumulation on the surface, we can also obtain the differential capacitance. So this is a very important experimental observable and also a key metric for capacitors. And then now I also want to show you something that was actually a little bit unexpected when we start this project. So this movie is actually showing a water dissociation reaction. So what happens is that in the simulations, we start with a tank of molecular water. But what happens is that because we add like high electric field, so eventually some water would dissociate and form a surface hydroxyl. You see there's a hydroxyl staying on the surface and a hydronium that is dissolved in the bulk. And we can also analyze this more like cleanly. So what happens is that for the initial state is 1 here, is the first step of this reaction. This happens by chemically absorbed water donating a proton to a physically absorbed water. So that's 1. And then it forms a hydronium. And then this hydronium then diffuse away. So it does not diffuse by the typical translational diffusion of water molecules, but it diffuse via the Grotius proton transfer mechanism indicated in 2. And if it's a salt solution, it can also transiently form a hydrofluoric acid. And also there are other times it forms like a Zundo cation. That's also possible. And at the same time, the hydroxyl on the surface is stuck on the surface, but it's very mobile in plane. And it is also diffused via a proton transfer mechanism. So basically a surface absorbed water molecule can donate a proton to the hydroxyl. One can also characterize the proton transfer rates for these reactions. So essentially the hydronium is much more mobile and the proton the residence time is a little bit smaller. And also and meanwhile, adding salt actually slows down the proton transfer rates. So I would like to conclude. So it's time that I bring out the slogan. So less is more. So latent Ewald summation, just by training on energy and forces, it can give you the correct long-range electrostatics. It also gives you the physical charges as well as electric response. With that, I would like to thank you.